this department.
Well, esse aplicativo que uma massagem.
I'm gonna turn off some microphones here.
Okay. Okay.
Before you start. Please keep your microphone off at all times, and if we have any questions, anyone has questions, just do it at the end of the lecture. If someone keeps the microphone open and do not close it, I'm gonna just take it out of the session kindly, but I will take it out of the session.
AKA
okay?
kick off the session.
Yeah, that's it. Go ahead, please.
So, good morning again, everyone, or good evening for those of you who are in Russia. So thank you, Daniel, for the introduction. My name is Guiherme Temporao. I am a professor in the Center for Telecommunication Studies in PUC-Rio, and I'm going to talk about a gentle introduction to quantum computing, aka quantum computing for dummies, as Daniel just said. So the idea for today is to try to tell you a little bit of what's going on in the quantum computing industry right now, and what exactly a quantum computer is, and what is it capable of doing. So I'll try to answer these questions. So currently, it's not unusual to see some news about quantum computing. Actually, every week or so, we have some kind of news, like a new company that decided to invest huge amounts of money in quantum computers, or a new quantum computer paradigm that has been created. Or, I mean, the last big news was in 2019, when Google claimed quantum supremacy. I don't know if you remember that, but it was like a big deal by that time, because quantum supremacy is a kind of situation where you can prove that quantum computers are better than traditional computers, that we'll call classical computers, in some tests. So Google has shown with some controversy that their quantum computers were much, much better than classical computers to solve a certain specific problem. And this was the beginning of, I wouldn't say that we have a revolution going on right now yet, but probably in the next years or decades, this revolution is going to become more important for our society. So, I mean, you have Google, IBM, Honeywell, many big companies that are investing a significant amount of resources in quantum computers from many years, and they are starting to show their results. And so every now and then we have this kind of news. Like IBM now has, I don't know how many quantum computers and so on. Well, the first question is, where are we? Where does quantum computing fit in our areas of knowledge? So there are three main areas of knowledge that we have to consider here. The first one is information theory. The second one, of course, quantum physics, or quantum mechanics, if you like. Quantum mechanics and quantum physics are synonyms, so we can use either word. And computer science, of course, talking about computers. So quantum information, which is the bigger area of knowledge that includes quantum computing, is exactly in the intersection between these three areas. So I'm going to talk about a little bit of each of these three areas before starting to talk specifically about quantum computers, okay? So the motivation actually started with Richard Feynman, which was a Nobel Prize winner in physics. And he published a paper in 1981 about the possibility of simulating physics. And by physics, he meant quantum physics using computers. So as you remember, in the beginning of the 1980s, computers were not as they are right now. Their processing power was much less than we have today. So physicists were still thinking about what computers could and couldn't do, in terms of simulating physical phenomena. And Feynman was very clear in his paper. It's impossible to represent the results of quantum mechanics with a classical universal device. So a classical computer, which is the kind of synonym for a classical universal device. So a classical computer cannot efficiently simulate quantum physics. He said impossible, but it's important to understand this word here, impossible, as it's impossible to make such implementation in a efficient way. It's possible to do this, but in a very inefficient way. So this was the starting point of quantum computing. And now we know, decades before the construction of the first quantum computer, people were already studying quantum algorithms. I mean, even when the idea of a quantum computer was still just an idea, it was possible to create algorithms for quantum computers. And when someday a quantum computer comes, it will be possible to implement these algorithms. And these two guys here, Peter Shor and Love Grover, created each one a very powerful algorithm, which are known today as Shor's algorithm and Grover's algorithm. Shor's algorithm is a quantum algorithm that is specific for factoring numbers. I don't know if you are aware of that, but many of our data security structures today are based on the difficulty of factoring numbers. For example, all kinds of cryptography that employ public key. I mean, when you have a public and a private key, such as RSA, they are based on this particular difficulty. It's a mathematical concept known as computational complexity. So it's very complex to create an algorithm that can factor a large number in a short time. No one has ever been able to do that. There's no proof, there's no mathematical proof that it's impossible, but we are trying for many decades and no one has been able to devise a classical algorithm that can factor a very large number in a small time. So if you take, for example, a number with 1,000 digits, okay, it's a very, very large number. A classical computer today, with today's computing power, would take thousands of years to factor. I mean, if we can consider that this number is the product of two prime numbers, okay? It would take thousands of years to find these two prime factors of this huge number. Whereas the quantum version using Shor's algorithm would take minutes to do the same thing. And there's another kind of cryptography that uses private keys, and the security of this cryptography protocols is based on the difficulty of finding a certain item in an unordered list. It's like if I take a phone catalog and I try to find the person who has a specific phone number, because the catalog is in alphabetical order. So it's very easy to find a name, but it's very, very hard to find a specific number because it's unordered with respect to the phone number. So if I have, for example, a very, very large list of another entries with 1 billion things, if I have a classical algorithm that would try to find what I want, in average, it would have to examine 1/2 of the entries. So the order of magnitude of this number of steps that I have to take is the same number of elements in my list. So if I have a list of 1 billion entries, I have an order of magnitude of 1 billion steps in my algorithm, a classical algorithm. However, Grover's algorithm, which uses a quantum computer, can do the same thing in the order of the square root of the number of steps, which is kind of around 30,000 steps. And there's a very big difference between 30,000 and 1 billion. So it's much, much faster. So these two algorithms are what are propelling forward the industry of quantum computers. Of course, they're only a small fraction of what a quantum computer can do, but maybe it's the most important thing for now, which because cryptography is a big deal. Once you have these two algorithms running in a quantum computer, you're going to destroy today's cryptography. So that's why we already have an area of research called post-quantum cryptography. It's a kind of classical algorithm that is immune to the currently known quantum algorithms. Of course, someone in the future can create a new algorithm that will attack this kind of new classical protocols. We never know. But as you can see, the quantum computer is a threat to our security standards that we use today for banking, banking transactions and secret communications and so on. Well, the story of quantum mechanics or quantum physics starts with the history of the search for the nature of light. Okay, Newton thought that light was like a collection of particles, but he didn't give any proof of that. And Huygens, which was a scientist from the Netherlands, he created a new theory that explained light phenomena from a very different perspective. He postulated that light was actually a kind of wave. He didn't know exactly which kind of wave, but he said, well, for all practical purposes, light must behave like a wave. Otherwise, we cannot explain the phenomenon of interference and diffraction. And it was not until 100 years later that Thomas Young made an experiment showing that Huygens' theory was right. And Young has shown that light could interfere with itself. And then if something is able to interfere, it cannot be a particle, it must be a wave. Okay, so in the turn from the 18th to the 19th century, it was proven that light was a wave, okay? By that time, nobody knew yet what kind of wave, but some bizarre kind of wave. Well, 100 years later, Max Planck, this was after electromagnetism has been established in the 19th century, Planck decided to study a very specific problem in electromagnetism, which some people thought it was just a minor thing that did not really deserve any serious attention because it was just, something that some small error or something. And Planck took it very seriously because electromagnetism was really, really great. It explained many physical phenomena. However, there were some things that were really bizarre. One of them was what we call black body radiation problem. According to classical physics, classical electromagnetism, if you take, for example, a metal and you heat this metal, for example, put it inside an oven, of course, we know that the metal will glow red, okay? And according to this theory, however, the metal would glow blue, or actually violet. And the amount of energy in the ultraviolet section of the spectrum, it would have infinite energy, which is something really bizarre. And nobody really believed in that. They thought it was just a small error. However, Planck found out that this was not a small error at all. It was impossible with classical electromagnetism to recover the correct results. Results which corresponded to what we have in real life. And in order to recover the reddish glow of a metal, Planck added something to the theory. He said that energy, electromagnetic energy, cannot be as small as we want. There is a minimum of energy. I mean, energy comes in packets, comes in multiples of a minimum energy packet. This was his contribution, but no one took him seriously because he couldn't prove that. He just showed that, well, if we consider this, then we can recover the correct results. Okay, but it was not very, very well liked because he didn't give any physical reasons for that. It was not until Einstein in the year of 1905, which is known as his golden year, when Einstein published 3 papers that changed the future of physics. And by that time, and this is a picture around that time, Einstein was working as he was working in a patent office in Switzerland, in Zurich. So he was not working as a scientist. He was working as a bureaucrat. And I don't know, in his lunch breaks, he was making revolutions to physics. And one of these revolutions was the explanation for the so-called photoelectric effect. It was one of these phenomena that did not have any classical explanations. And what Einstein did was he used Planck's idea of this minimum amount of energy, and he went one step further. He said, actually, light is comprised of particles, and each particle has this minimum amount of energy that Planck said. In the future, those particles were going to receive the name photons. So in order to explain the photoelectric effect, you have to consider that light is comprised of particles. So as you can see, there's a problem here, because I have just said that in order to explain interference phenomena and diffraction, you have to consider that light is a wave. But there are some other things that if you say that light is a wave, you don't have any explanation. You must consider that light is a collection of particles. So this is where things become strange. Okay, this is the heart, the core of quantum physics in its beginning. It's the wave-particle duality. So what's going on here? Let's think about this very, very simple experiment. We have here one photon, okay, one particle of light, and this photon is traveling to the right, okay, from the left to the right. And here there's a thing called a beam splitter. This is actually a mirror, okay, it's a kind of mirror, but a normal mirror reflects everything. I mean, 100% of the light that hits the mirror is reflected. The beam splitter is a little bit different. He reflects only 50% of the light. The other 50% it lets go through it, okay, unaltered. So there are 2 possibilities for a photon. A photon can either go through the beam splitter and be detected here at this place. This is a detector, a photo detector. Okay, it's a detector which is sensible to one photon. This really exists, okay? This is something that you can buy. So it has this first possibility. And there's a second possibility that the photon will reflect at the beam splitter and be detected here, detector D2, okay? And what we find out when we do this, when we do this experiment, of course, the photon cannot split in 2 parts. If you launch classical light here, of course, light will split in 2 parts of equal magnitude, equal power. But when you use only one photon, the photon cannot be split in 2 because by definition, the photon is the smallest amount possible of energy. If you could split a photon in 2, then you would contradict your own definition of what a photon is. So it's impossible to split a photon. So what happens is the photon either goes through or it reflects at the beam splitter, okay? If you repeat this experiment many, many times, we find out that there's a probability of a photon be reflected and a photon be transmitted that is equal to 1/2 or 50%. So 50% of the times the photon will go one way, 50% the other way. So this was a very big revolution in physics, because for the first time, physics was not deterministic. Newtonian physics, Newtonian mechanics, what we call classical mechanics, is deterministic. If we know the initial conditions of a physical system, we can calculate the future. We can calculate the trajectory of a particle in the future if we know the correct initial conditions. But here in quantum physics, it doesn't matter if we know the initial conditions, because different things may happen at random. So it was the first time where randomness was considered a part of the physical theory. Okay, so it was a big revolution, really. The physicists had to change their way of thinking about nature. So now we know that randomness is an essential part of nature. Okay, the universe is not deterministic. There's something really random about the universe, and you can earn money with that. People are already doing that for more than a decade, actually. You can buy this kind of thing. It's called a quantum random number generator. Okay, this thing here, this module, like don't know, 10 or 15 centimeters long. Okay, it has a USB connector. It costs around 1,000 euros, and it works exactly like that. Okay, there's a beam splitter, there's a laser. I don't know if it's a laser or a LED. I'm not sure. And there are two photodetectors, and it generates randomness like that. So it's a way of creating random numbers without resorting to algorithms that are very complicated and that cannot generate true randomness. They create like we call pseudo randomness. This creates true random numbers. And you know what are the biggest clients of this company, of ID Quantique? This is a company in Switzerland, okay, in Geneva. They sell this kind of things here. Their biggest client is the lottery. I thought it would be the army or the banks, you know, the Swiss banks, but no, it's the lottery, because I think the lottery is trying to, you know, to become more transparent to the client, so they know that when they do a prize drawing, they can trust the lottery. You know, it's not something that is, you know, some shady business. Not a scam or any kind. It's a real drawing. I mean, based on pure chance. And when you are based on quantum random number generators, you give some like a physical explanation for the randomness. So they're telling you, look, here's where I extract my randomness. It's just a physical phenomenon. So here, of course, the light behaves as a particle, because the photon is every time found just one place. It's either here or here. It's never in two places at the same time. A wave can always split in many parts. It's no problem for a wave. But for a particle is always concentrated. However, if we make a very slight modification, it seems a little bit complicated, this drawing here, but actually it's not. What I'm doing now, I'm using two beam splitters instead of one. There are these two gray things here, that are beam splitters, and these two black lines are regular mirrors, okay, like mirrors we have in our homes. Okay, there are mirrors that reflect everything that hit on them. So we still have only two paths here. The photon which is here on the left in the beginning, it can go up, or it can continue to move forward here to the right. Okay, so if we trust that it's just a random physical event, that, well, the photon, when it hits the beam splitter, it kind of decides which way it should go. Okay, so imagine you are the photon is going forward. Oh, there's a beam splitter. I have to make my mind now. I have to decide whether I'm going through the beam splitter or if I'm going to reflect on the beam splitter, okay? With 50% probability. So if we imagine this picture, the photon will be here at this path here 50% of the times, and here 50% of the times. And then the same thing will happen here. They will find a second beam splitter, and again, the photon will choose randomly which way it should go. And in the end, what we expect in theory, that 50% of the times the photon will be found here in D1 and 50% in D2. And however, this is not what happens at all. What happens is the photon it's always found here in D2. It never comes here to D1. So if you do this experiment, you'll find that every time you put a photon here, it comes here for D2. So the probability of getting detection in D1 is 0. The probability of getting detection in D2 is 1. I mean, 100% of the times the photon will be found here. So you cannot explain this if you think of the photon as a particle that makes its mind every time it interacts with a beam splitter. So in order to explain this thing here, now we have to consider the photon as being a wave. Okay, if we use a wave-like model for the photon, it comes very, very easy. It's a very straightforward calculation. You can show that the photon will always come here because of the phenomenon of interference. You have destructive interference here in D1 and constructive interference in D2. And we'll only see the photon where there is constructive interference. Okay, so as you can see, the photon is neither a particle or a wave. It's at the same time a particle and a wave. And it, depending on the experiment that you do, it behaves one way or the other. So this is the wave-particle duality, and quantum computers are based on this. At its heart, quantum physics depends on the wave-particle duality, okay? So, of course, it's not the most weird thing that we can think about quantum physics, but it's maybe the first shocking thing. All physicists say, including the Nobel Prize winners, they always say, well, quantum physics is really impossible to understand. You can get used to quantum physics, but it's really, really hard to understand what's going on. So this is what concerns quantum physics for the moment. The second area of knowledge that was mentioned in the beginning is information theory. And information theory was also a theory created in the 20th century. Okay, quantum physics was developed entirely in the 20th century. And information theory as well, it was created by this guy here alone. It was called Claude Shannon. What Shannon did was he managed to create a quantifiable measure of information. Okay, information was considered as something really fuzzy before him. So it was very, very difficult to define what information is. What Shannon did was, well, actually information is something that is always in respect with the knowledge of an individual. So if I gain knowledge, if I was unaware of something, and then I become aware of something, then I gained information. So information is like a change of state. When you are unaware or you don't know something, and then you know something. This transition from not knowing to knowing is information. Okay, and so it's not related to semantic aspects of communication. Okay, doesn't matter. For example, usually in the communication scenario, we take two people who are trying to communicate. Instead of using letters which are boring, like a person A is trying to talk to communicate with person B. This is boring. Normally, people give names to these people. So A we'll call Alice and B we'll call Bob. Okay. So Alice is the person who's trying to communicate something to Bob. Alice is what we call the transmitter, and Bob is what we call the receiver. So Alice is transmitting information to Bob. Bob is receiving information from Alice. Let's say that every day, okay, in the morning at 9 o'clock, Alice sends the word, I don't know, potato to Bob. Okay. Every day, potato, 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 every day, at the same time. What Shannon says is there's no information in this scenario, because we can consider that potato is a thing that has information. It would be different, for example, from saying strawberry, or I don't know, earphones, or I don't know, anything. Potato has a semantic aspect, okay? We know what a potato is. But for the purpose of communication, it's irrelevant, because if Alice every day at the same time says the same thing to Bob, there's no information gained for Bob, because Bob already knows in advance that Alice is going to tell him potato. So he gains no information at all. So in this scenario, we know that Alice is codifying the word potato in bits and sending bits to Bob, but these bits contain no information at all, because Bob already knows what's going to happen. So the information gain is zero. Okay, this is the revolution that Shannon started alone in this paper of 1946. So information only depends on the probabilities of occurrence of the symbols. If something has probability 1 of happening, it has no information at all. So Shannon defined this thing here as a measure of information, which is now known as Shannon entropy. Okay, so the entropy of information is something that tells us, actually, it's a kind of a measure of uncertainty. If you are uncertain of something, then that something has information. Because when I make a measurement, when I receive this something, I will gain information. So before I receive the data, I cannot be aware of what is it. Otherwise, I won't gain any information at all. This is the revolution of Shannon. Okay, information theory is based on that, and of course, quantum computers are also use this approach for information, slightly modified, of course. And third, we cannot neglect the area of computer science, which had one of its founders, as Alan Turing, okay, the British researcher that created what we call today a Turing machine. Actually, what Turing was trying to answer the question of what are the kinds of computation that we can do? What can be computed? This is the question that he was trying to answer. Can we compute everything, or there are some kinds of things that cannot be computed? So what has shown that we can create, this was really, really new. It also happened in the 20th century, okay? These three big areas of knowledge, each of them was created recently, 100 years ago or less. So Turing has shown that you can build an universal machine that can compute nearly everything. Okay, not everything, but nearly everything. He can compute everything that can be computed. There are some things that he has shown that cannot be computed, but among these things that can be computed, his model, his Turing machine, could make a computation. It was really new. Before that, people thought that you had to build different machines for different problems. Okay, so you have here one machine for, let's give an example here, one machine for adding numbers, another machine for multiplying numbers, and so on. What he has shown is, no, we can have one integrated thing, which is a Turing machine, okay? And the so-called Church-Turing thesis says that every function that could be naturally considered as computable, it's really fuzzy here, the language, but what he meant was everything that is physically implementable can be computed by Turing machine, okay? Things that cannot be physically implementable not necessarily can be computed by Turing machine. But this was really also a revolution that was very, very helpful for building of computers. Okay, there's a movie, a very interesting movie on Alan Turing that came a few years ago. I think it's called The Imitation Game. For those of you who hasn't seen it before, I recommend it. It's very interesting. It's about the life of Alan Turing. And he's worked against the Nazis in the Second World War. So when we get everything together, these three big areas of knowledge together, the intersection of them, there's a saying by this physicist here called Rolf Landauer that said, all information is physical, okay? When we think about information today, we think about bits, right? Megabits, gigabits, megabytes, oh, I have this, USB drive that it's able to store, I don't know, 10 gigabytes of data. But when you think about information, you think about bytes and bits. But we can never forget that all information is physical. I mean, those bits, they're coded in some physical system. The information is not, something like it's not something that is detached from the physical world. It's really something that's encoded in some degree of freedom in the physical world. It's not an abstract concept. It's like a physical concept. So it's interesting for quantum information because the research goes in two opposite ways. Because if all information is physical, then of course the laws of physics have many things to say about the laws of computation. Of course, if computation is something that you have to deal with physical systems, we cannot have some weird behavior that would violate the laws of physics. Of course not. So if you learn about the laws of physics, we can know a lot about the laws of computation, and vice versa. If we know the laws of computation, we can have insights on the laws of physics that are below them. Okay, so we have this two-way research field, which is very interesting. And here we can make the difference between a classical and a quantum system. What is a classical bit? What we usually call bits is just a classical two-level system. Something that can be in two states, like two voltage levels. Okay, like we can have 5 volts for a bit 1 and 0 volts for a bit 0. Or we can have a light bulb turned on for a bit 1 and turned off for a bit 0. Or a magnetic spin in a hard drive, which I don't know, it's a spin clockwise direction. It's a bit 1 in the counterclockwise direction, a bit 0. Or you have a charge in a capacitor in a USB drive. And if the charge is present, it's a bit 1. If the charge is absent, it's a bit 0, and so on. All bits are encoded into physical systems, okay? In this case, classical systems. And the quantum bit, that we call for short a qubit, is just a quantum two-level system. So it's a system that now is encoded in a very small or fundamental particle, like an atom or a photon or a neutron or so on. Okay, for example, energy levels of an atom. We can, for example, say that one of the energies, if the electron is closer to the nucleus, it's going to be a bit 0. But if it's in an orbit that is further from the nucleus, then now it's at a state called 1. So we can have two states in an atom. The difference is here in quantum physics, one of the postulates of quantum physics actually says that you can have a superposition of these states. So in classical physics, you cannot have a light bulb which is at the same time turned on and turned off. It's either in one of these two states. But in quantum physics, you can actually be in something intermediate between these two, which we call a superposition of these two states. Okay, so this is the expression that we use. We have here these numbers, which are complex numbers. Actually, it has a real and imaginary parts, and they're called the probability amplitudes. Their value squared corresponds to the probability of measuring one state or the other. Okay, and we can make an analogy to the surface of a sphere. Okay, in classical physics, you have only two possible values for a bit. For example, if we understand the sphere as a globe, then at the poles of the sphere, the North Pole, the South Pole, we would have the classical values of the bits, 0 and 1. But in quantum physics, every point in the surface of the sphere is a possible state. So each point of the sphere corresponds to a different physical situation of the atom, for example, in this case. You will not either at one pole or the other. You are somehow in the middle of the two, which is some way of interpreting what quantum physics has to say about it. But it's more complicated than that, actually. Because you could also say for classical physics, well, I can have a light bulb turned on and turned off, or I can have a light bulb like in the middle, like a dimmer. We can use a dimmer to put the lamp in an intermediate state between turned on and turned off and say, oh, okay, I also have here a superposition of the two states. It's not the same thing at all, okay? And trying to show you this. Here is the example we had before with just one beam splitter, okay? I removed the second beam splitter here, so we have the first example. The photon can be divided in two here, this first mirror, okay? First beam splitter, and it can go either here for D2 for the upper path or D1 for the lower path with 50% of probability. What quantum physics tells us is the photon doesn't make any choice when he goes through this beam splitter. It actually becomes in a superposition of taking both paths at the same time. So when a photon goes through this kind of mirror, or partial mirror, it goes, it's reflected and transmitted at the same time. But when we make a measurement, this situation collapses into a single result, which is called the measurement problem of quantum physics, or the wave function collapse. Okay, I cannot go into any details on this right now because we don't have time for that. But when you make a measurement, we never find a photon in two places at the same time. We always find it in one place. Okay, so this is a kind of a superposition. If we call this path here a state 0, and the other path is state 1, so it's not superposition of states 0 and 1, okay, with probability amplitudes, which are the square of these numbers here, which are 1/2, okay, so 50% probability each. The mathematical way of representing this state, and in this sphere representation that I was telling you about, it could be like a point in the equator of this globe. It's a halfway between the poles, okay? It's neither 0 nor 1. It's in the equator. It's in between the two values. So, okay, it can be a superposition of two places, but there's an extra assumption here that I can make a different measurement. I can put a second beam splitter here. And as you remember, whenever we put a second beam splitter here, then the photon is always found here in D2. It's never found in the position 0. So what does this mean? There's always a measurement basis. I mean, it's a way of measuring the qubit where the value of the qubit is well defined. You have 100% probability of measuring it in a certain position. Okay, this is what's different from classical physics, because the qubit can be in two places at the same time, okay, two states at the same time, but there's always a way of measuring it that has a deterministic result. To make the correct measurement, I can always predict with certainty what will be the output of my measurement. And this is something that you cannot do with classical physics. It's impossible. Okay, this is what we call coherent superposition. Okay, it can be in two states at the same time, but at the same time, you can make a measurement that is non-probabilistic, it's deterministic. This is what we call a qubit, okay? It's a coherent superposition. Okay, it gets weirder. We can have quantum entanglement. Quantum computers use quantum entanglement a lot, okay? For the more advanced algorithms, you cannot neglect quantum entanglement. So entanglement is a completely different thing. It's a kind of joint state between two photons or two atoms or two electrons and so on, where the joint state is well known, but the individual state is not well known. Okay, it's not in a coherent superposition of anything. So in this example here, you have a superposition of two possibilities. Either the particle on the left is at state 0 and the particle on the right is at state 1, or the opposite. The particle on the left is 1 and the right is 0. So if you try and say something about the nature of the state of one individual particle, it has no definite state. So quantum physics has nothing to say about this individual particle here on the left or to this individual particle on the right. It can only say something about the collective state. And this is something that's completely different from classical physics. Of course, in classical physics, if I know something about the set of many different things, for example, if I have a collection of cars, okay, I have 10 cars, and I know everything about the 10 cars. Of course, if I want to look at a specific car, I'll have all the information about on this car. I mean, the speed, the position, and everything about that car at that moment. Okay, if I know the information, the complete information about the 10 cars, at any time I can, well, I'm going to just look at one specific car, and of course I'll get a specific answer about the velocity and the position of the car. Okay, it's very, I mean, it's kind of obvious, right? But not for quantum things. If two things like electrons or photons are entangled, there's only one description, which is the collective description. You know that they are always going to be found, in this example, in opposite values. If you find that the first one is 0, the second one will be 1, and vice versa. But the first one is not 0, neither 1, and the second one, the same thing. They're not in specific states. They are kind of random mixture of states. It's as if these values don't exist at all until you make a measurement. So they have no physical reality. This is something very bizarre that only happens in quantum physics. Okay, you can have quantum states that have no physical reality until you measure them. It's like you order a quantum pizza, for example. The quantum pizza would have no flavor. It would be a random mixture of different flavors, and once you look at the pizza, then it will collapse to a flavor, like pepperoni, okay, or margarita. It's really bizarre. It's something that we don't have in classical physics. Okay, so the collective properties of the particles are well known, but individual properties have no physical meaning. And Einstein, of course, didn't like anything of that, because these two particles can be arbitrarily distant from each other. You can have, for example, Alice with a particle here, and Bob with a second particle in, I don't know, in a different galaxy, which is entangled to the particle with Alice. And whenever Alice finds something about her particle, then she instantly knows what Bob is going to find many thousands of light years distant. For example, 500 light years distant. So they're really, really far from each other. And however, this kind of this, what Einstein called spooky action at a distance. He said in a letter to Max Born, I cannot seriously believe in it. In it, he meant the quantum theory, because the theory cannot be reconciled with the idea that physics should represent a reality in time and space free from spooky action at a distance. So somehow what's happening to particle A is creating an instantaneous influence on particle B. And this violates Einstein's locality assumption, which was one of the bases of his general theory, the special theory of relativity, okay? That nothing can move faster than light. So if you have two things that are separated by 500 light years, if something happens here in A, it will take 500 years to communicate to B, because that's the time light takes to move from one place to the other. So it cannot happen instantaneously. However, in quantum physics, if something instantaneous seems to happen. And Einstein and his colleagues tried to show that quantum mechanics was not complete, okay? So that was something in the representation of quantum mechanics that was not there in the theory. And they published this paper, which had a big repercussion. And it's important for us to understand that these correlations are not like classical correlations. There's this physicist called Reinhold Bartolman, and he's a really bizarre guy because he always wears socks of different colors, okay? This is an actual picture of him in a conference. So as you can see here, he has a green sock on his right foot and a pink sock on his left foot. And you can say, well, Bartolman's socks are always anti-correlated. If you know the color of one sock, then you instantly know that the other sock has a different color. Of course, you can take these two socks and send them to opposite sides of the galaxy. okay? And someone finds one, okay, I have found a pink sock. So I instantly know that the other sock is not pink. So what's weird about that? There's nothing weird about that. Okay, we're getting instant information. It's not weird. The problem is that on quantum physics, as you can remember, the color of the socks is not well defined from the beginning. The pair of socks has a property that they are opposite in color, but each sock does not have a predetermined color. That's the difference. So if you make an analogy, it would be like, I have a sock here that is a mixture of green and pink, but I don't know which color it is because the color doesn't exist until I make a measurement of the color. When I make a measurement, then the act of measuring the sock, you create a color. And instantly, the other sock will collapse to the opposite color. This is what happens in quantum physics. So it's not just a matter of classical information, okay? It's really different. There is a distinction between classical and quantum ignorance. And John Bell has shown that reality is incompatible. This local realism model of Einstein, Podolsky, and Rosen is incompatible with quantum physics, okay? He devised a very simple experiment. I'm not going into the details here. That is called Bell inequality, okay? Local realism satisfies this equation. This quantity here is a kind of statistical quantity. If you're making different measurements on different things, could be thoughts, could be billiard balls, could be electrons, could be pizzas. It doesn't matter, okay? There are pairs of things being generated, and Alice and Bob are making measurements on them. And this value S with a statistical result of measurements, it's always bounded above by 2. The absolute value is always smaller or equal to 2, but quantum physics can go above this value. You can find a value of 2 times the square root of 2, which is approximately 2.8, okay? So entanglement violates Bell's inequality. So somehow reality is non-local. Somehow what you do here in Alice will cause something instantaneously to change in Bob's position, 100 or 500 light years away, but in such a way that you cannot communicate faster than light. Okay, so somehow the theory of special relativity of Einstein is still preserved. You cannot send information faster than light, but this shows us that reality is really bizarre, and quantum computers work in this kind of bizarre reality. Okay, I'll skip this slide here. I'll come back to it later if we have time. So what the quantum computer is, finally. A quantum computer is nothing like a classical computer. You can imagine a quantum computer as a series of experiments that are performed, for example, in a table. In this drawing here, it's an optical table with lasers and detectors and mirrors and things, and they have equipment, and you have a classical computer here being operated by something, by someone. And so the quantum computer now, as we know it, it's a really big thing. It's not something that we can carry in our pockets or even put in our rooms. It's like the previous classical computers that would take buildings. Decades ago, when the classical computer was created, okay, it was huge. So the same thing is happening to the quantum computer. The quantum computer now is something like a really big thing, comprised of many smaller components. And what is the idea of the quantum computer? That we can create somehow isolated quantum systems. This is really difficult because if you, for example, take a molecule of hydrogen, okay, in this room here, right now, this molecule, of course, will behave in the way of quantum physics, but it's not isolated from the rest of the environment. So these atoms or photons or whatever we use to implement the quantum computer, which are going to use as the qubits, okay? As I said, information is physical. So the quantum information is going to be encoded in these quantum particles, okay? The first thing we have to do is to isolate these particles from the environment. And this is the hard part. because these interactions are really difficult to, completely erase every kind of interaction between its particle and the environment. And once you have done that, for example, you have two atoms, okay, or two electrons, and you have managed to make them, decorrelated from the environment. So the first thing you have to do is you have to initialize them in a well-known state. This is important, okay? You have to know where the initial state of your machine. Otherwise, you won't know where the machine is going to lead us in the future. So we have to initialize them. For example, okay, if I'm talking about energy states, if I have two energy states, for example, I'm going to initialize the two particles in the lowest energy level. Okay, so I know they are in the lowest energy level. I somehow have to know they are in the lowest energy level. So this is called the initialization step. Then we, for example, use a laser beam or something, a magnetic field. It's going to depend on the practical implementation of the quantum computer. You create a superposition between these particles. Okay, so they are at the same time at the two energy levels. In this example, they are halfway between energy level 1 and 2, like the photons were at the same time in two paths. Here, the particles are at the same time in two different energy levels. Right? And then we use what is called the oracle, which is we let them suffer what we call unitary evolution in time, according to some Hamiltonian is the correct way of talking about that. It depends on how you will implement the modifications you want to do in your system. Okay, so you let your system evolve naturally according to some scenario that we have created. For example, we apply some magnetic field or electric field or so on, and we let the particles evolve in time, naturally, okay, during a certain time. And then we make them interfere against each other. We have to devise some way of physically making them interfere, like, for example, in the previous example of the Mach-Zehnder interferometer, where we took a second beam splitter and we make the two paths of the photon to interfere and create some interference pattern. Okay, so we have to somehow make these two particles interfere with themselves. Okay, the states have to interfere with each other. And then we make a measurement. And when we make a measurement, we recover a certain classical result, okay? So all the results that we get from quantum computation are classical results. We don't have quantum results. The results that we want are always classical. So in the end, you have just a number as a result. You won't have a superposition of things as the result of quantum computation. No, you have a definite result. So we have to think about smart ways of doing this interference in this preparation, this oracle, etc., to make this measurement result meaningful. This is actually the challenge, the biggest challenge for quantum computing. You have to devise these algorithms that can do these smart interferences and preparations. So when you measure something, you gain some information in a way that's much more efficient than a classical way, okay? And these results can be probabilistic as well. Sometimes maybe the result of the measurement would be something that doesn't mean anything, like an indeterminate result, okay? A result that says nothing. Sometimes quantum computation requires this kind of algorithm. It's called a probabilistic algorithm. It's an algorithm that sometimes gives you a response, sometimes doesn't give you anything as a response. It's not a problem because we can do this many, many times. Usually these algorithms are run many times. You initialize the particles in a certain state, and you do the same thing many, many times. You don't do it just one time. So it's not a problem if the algorithm is probabilistic. If it doesn't happen the way we were expecting, you just do it again. Okay. So just to give you an example of the quantum advantage, of course, I have already gave you two examples of applications in cryptography, where a quantum algorithm can be much more efficient than a classical algorithm, okay, in terms of breaking the security of a cryptographic system. Let's say you want to simulate a quantum state of 36 particles with two states, which I mean 36 qubits, okay, 36 systems which have two levels, like 36 atoms with two energy levels, or 36 photons with two paths, and so on, okay? If I have a classical computer, the important thing here is that the number of bits that I have to use to simulate this is really big, because these particles here, if this value of n in this case is 36, okay? So if you have two states, 36 particles with two states, they can be in any combination. The collective state can be at any of these two states, and you have to consider all possibilities, which are 2 to the power of n, okay? But in quantum physics, as I have told you, we use complex numbers. So each one of these states uses two real values, which is the real part and the imaginary part. So we have to multiply this by 2 because I have two real numbers. And a real number is represented in a computer as a double, okay? For those of you who are of computer science, is a kind of number that it can have decimal places and so on, okay? If you do this calculation with the usual amount of bytes for representing a real number, you have 1 terabyte, okay? So you would need a computer with 1 terabyte of RAM memory. Okay, I am sure no one here has this amount of power. It's impossible. Okay, it's not impossible for us, I mean, the users of computers. Of course, you can create a supercomputer with 1 terabyte of RAM. Yes, it's possible, but it's important to see here that we are only simulating 36 particles, not a huge number of particles. Okay, if you increase the number of particles, this doubles every time you add a new particle. So if you have 37 particles, you need 2 terabytes of memory, okay? For a quantum computer, you only need 36 qubits. That's the difference. You don't need 1 terabyte of RAM memory. You just need 36 qubits. Of course, there's a difference here between what we call logical qubits and physical qubits, but I won't go into this details right now. So this is a no-go, okay? The first case here, bye-bye. It's impossible to do this in a feasible way. And here, well, building a quantum computer with 36 qubits, it's already in the horizon of these companies that are already producing quantum computers, okay? IBM is getting close to 36 qubits. They are not yet there, but maybe in 5 years. I don't know. This is called the analog quantum computing. It's a kind of, actually it's the weakest kind of quantum computer. It's a quantum computer that is used just to make simulations. Actually, it's not the weakest, it's the intermediary kind. I have here, I'm going to show you these differences. But a quantum computer must satisfy some criteria, okay? I won't get into any details here, but it has to be scalable, of course. If you're going to add more qubits, it must be possible. You have to be able to initialize the qubits in a simple state. The decoherence times have to be long enough. I mean, decoherence is the interaction with the environment. You have to keep them isolated from the environment for a time which is long enough for making all the calculations. You must have a universal set of quantum gates, which are the operations that you can do with these elements. You have must have the capability of measuring specific qubits. The conversion between stationary and flying qubits are to communicate between quantum computers and to make a network of quantum computers. They must be able to communicate. And these flying qubits, their transmission must have a high fidelity. I mean, what one computer sends must be very close to what the other computer receives. The loss of information must be low, okay? It's very hard to implement this all criteria. This is a slide from IBM. showing the kinds of quantum computers. You have the quantum annealer, okay, which is a very specific quantum computer. It's not a universal quantum computer like our computers. When you think about a computer, we think about programming the computer to do anything we want. Okay, we can make a spreadsheet, we can create a game, or I don't know, a simulator, and so on. For quantum computers, that depends. There are some specific kinds of quantum computers that solve only one problem. This is called the quantum annealer. There are intermediate quantum computers that are able to make this kind of quantum simulations. Okay, they're called analog quantum. But the kind of quantum computer that we really want to see working is the universal quantum computer, where we can really make a program. We can create algorithms for them, any algorithm we like, and they can implement these algorithms. That would be closer to what we call a computer today. So we have this way of dealing with quantum computers. People that work with quantum computing, they don't need to understand exactly what happens in the physical level. We can work in a higher layer of abstraction and work with, some operators in linear algebra, and we can deal with this quantum phenomena using abstractions like black boxes. We don't know what's inside the black box. It doesn't matter. We only need to know what happens if we do such and such with the black box. Okay, so I have elements, 1 qubit gates, 2 qubit gates, measurement gates, and so on. If we know how to arrange these elements, we can create a quantum circuit, okay, which is a quantum algorithm. This is the way how we program a quantum computer now. It's kind of, you make a representation, a high-level representation of a circuit, and you implement this circuit on the quantum computer. Okay. And IBM, I won't have time to talk about that, but IBM used a kind of qubit that's called a superconducting qubit or a transmon qubit. Okay, each company uses a different kind of technology. There are companies that are pursuing optical quantum computers. Others use superconducting qubits in different ways. They have these transmon qubits or different kind of superconducting qubits. Nuclear magnetic resonance for some computers, ion traps for some others, and so on and so on. There are many technologies that can be exploited to create a quantum computer. Okay, this it was an example that I have taken from IBM. Okay, IBM is kind of a step forward now in comparison to the others, because anyone here can program a quantum computer right now if you want. They have made available a kind of interface which uses this kind of framework for Python. Okay, so if you know how to program in Python, you actually don't have to know Python a lot. Just a little bit, the basics. And you can use this framework called Qiskit. Okay, Qiskit is a language where you can build these circuits and make measurements and, making everything. So you can create simple quantum algorithms using Qiskit and run these algorithms in an actual quantum computer from IBM. So IBM has selected a few of them quantum computers, which are the oldest ones, with a small number of qubits, okay? And you can actually use these quantum computers right now. It's available to everyone. It's free. Anyone can go there and try. It's called the IBM Quantum Experience, okay? I don't work for IBM. I'm not making any kind of marketing here, but it's because it's the platform that's more easily accessible, okay, by everyone. And we also have, for example, Microsoft. Microsoft, they have this solution, the Microsoft Azure, which is their cloud solution. They always have the quantum version of the cloud solution. So we can also use Microsoft's quantum computers for free. But you don't use Qiskit, because Qiskit has been created by IBM for their computers. Use Q#. Q# is a different language. okay, for programming quantum circuits. So as you can see, there's no standard yet, and probably there won't be any standards for a long time. And the same way we have different programming languages today. You have Java, you have Python and PHP and C and so on and whatever. We'll have different languages for programming in quantum computers. Okay, so you can also check Microsoft's website if you want to have more information. So, in conclusion, I have talked too much now. First conclusion, quantum information, which includes computing, is inherent to the multidisciplinary area. So we have people from many different areas of knowledge working with quantum computers. We have physicists, engineers, and computer scientists, and so on, because it involves many different sides. It's a really interdisciplinary area. So you don't have a person that is specific for a job, to work with a quantum computer. You need a plurality of formations, which is really interesting for this new area. Okay. Second conclusion: quantum computers are already a reality. There are already many quantum computers out there. However, they are really costly. A quantum computer can cost millions, hundreds of millions of dollars to build. So it's not really possible to imagine yet personal quantum computers for us in our homes. This probably won't happen for a long, long time. But these solutions where a quantum computer can be shared by many people using a kind of cloud solution, this already exists. Okay. Third conclusion, quantum algorithms can have performances with no classical analogs, which is called the quantum advantage. So there are specific algorithms that perform much, much faster, much better than classical algorithms. And this is where the research is focused. We have major technical challenges limiting the number of qubits. We don't have yet, for example, in order to implement Shor's algorithm and destroy current technologies cryptography, because we would need a quantum computer with 1,000 or more qubits, okay, logical qubits. It is really, really far from the reality for the moment, because it's really, really difficult to separate 1,000 quantum particles from the environment and at the same time make them possible to interact with each other, like create entanglement between them at will. Really, really hard to do that. So these technical challenges are maybe the most important things happening right now in quantum computing. There are many practical implementations being considered. As I said, there's no final solution for a quantum computer. Okay, there are many technologies being studied yet. This is really important. Quantum computers will not replace classical computers. This is a question that I hear sometimes. Oh, so my classical computers will be replaced by quantum computers in the future? And the answer is no, because there are certain things, certain tasks that classical computers do much, much better than quantum computers. For example, if you ask them to calculate 1 + 1, okay, a quantum computer, you can actually ask this question for a quantum computer. You have to create a quantum circuit that creates this problem, and it will give you the answer too, okay? But it's much more inefficient than a classical algorithm that just adds 1 and 1, okay? So quantum computers, they are universal, but in the sense that you can create any quantum algorithm that has an advantage over classical algorithms. It doesn't make sense to use a quantum algorithm to replicate a result that can be achieved with a classical machine. Okay, it doesn't make any sense because you're using a machine that costs hundreds of millions of dollars to do something that a calculator, a pocket calculator can do. Nonsense. Okay, so we'll never actually replace classical computers. They will probably work side by side. Okay, so this is the end of my talk. Thank you so much for your attention. And if you have any questions, I'm sorry, I didn't look at the chat. Maybe I can do this right now. I'm going to see if there are any questions here.
Guilherme, thanks a lot for the lecture. You know, I lost myself in the first formula, but you know,
Okay.
you shouldn't have brought numbers, man. But okay, it's fine. It was perfect and elucidating. But you know, I don't know about you guys, but I'm never gonna write about quantum computers. And you know, I think it's above my. I need to study engineering with Guilherme sometime. You know, maybe do a master's degree in engineering because it's a hard topic, and I see it's still evolving. It's an ongoing topic, and it's really hard to write something about, you know, something it's not done yet, especially if you try to mix with the law field and regulation or anything.
Exactly,
So that's
exactly. Because the applications of quantum computers are not yet established. So if you think about law, for example, I have no idea how a quantum computer could be useful for an application in law, but certainly someone will find out a way of using it. I don't know.
maybe AI. I don't know, quantum computers and
Maybe, yes,
AI for
yes.
decision making. I don't know if it's, you know, just
Yes, it's an area of quantum computing. I have not talking about that, but there's an area called quantum machine learning. Okay, quantum machine learning is a thing, is an area of research, and it's exactly the AI version for quantum computers. So there are some problems in machine learning that are much easier, faster to do with quantum computers. For example, there's a problem of matrix inversion, which is really useful for machine learning that depending on how this matrix is constructed, the quantum computer can make this inversion millions of times faster than a classical computer would do. So yeah.
Matrix inversion to me is that thing that Neo did, you know, in the movie. That's the Matrix inversion. But other than that, you know,
Yeah. Oh, I'm sorry, but it's not that
these guys
cool.
are young. They don't even know the movie. The movie is from 1999. They
What? They don't
weren't
know the
even born.
movie?
Of course we do. We saw the movie. Everybody knows Matrix.
Yeah.
Daniel, can I ask some questions to our guest here?
Take it
Daniel,
easy, man. Take it easy, Bernardo.
just one question. Just literally just one
I'm
question.
kidding. I'm kidding.
Right. So there was a point where you talked about quantum random number generators, right? That you're saying they are commercially available, and that was interesting because of a long time ago, me and Daniel, we were researching about this topic about virtual worlds, and I came into this whole game monetization thing around using a random number, loot generators, and that kind of stuff as a reward for players. And
Bernardo, Guilherme is a player too. Okay, so
oh,
he knows what you're saying. Yeah.
perfect. So, is that currently being used in virtual worlds? This technology of quantum random number generators, or is this just something specific for that example you just said about lotteries?
I don't think so because, well, it's expensive. Okay, so one generator costs 1,000 euros. Okay, it's not so much expensive for a company. Okay, for a company, it's actually very cheap. For final users, it's expensive, and we have no reason to use a quantum number generator. Okay, we can use a pseudo random number generator, and we're fine with that. And I think this different implementations, they of course they could use quantum random number generators, but the question is why would they use it? Usually they use it for adding transparency, for showing the customers that it's fair. It's like a fair dice roll, and I can prove it that it's a fair dice roll. Maybe from this point of view of fairness. Oh, okay. We are already getting closer to the law. Okay, fairness.
Yes, exactly. That's exactly where I wanted to go.
Yeah.
Because...
Yeah. Okay. Yes, it could be used. Of course, it could be used. Okay. I just mentioned the main applications. Okay, so the main applications are lotteries, and of course there are also some uses for banks and the army and so on. But lotteries are the biggest market for now. But yeah, if you would find some way of using random numbers that are created in a very transparent way, like for example, there's a protocol in quantum communications that you can create a fair coin toss over distance, which is something impossible using classical technology. Okay, if we play here a coin toss game like heads or tails, one of us can always cheat. It's always possible to cheat, like adding a delay in the channel, and you know beforehand my answer, and you prepare your coin otherwise, and then you show me your answer with this delay. For example, you cannot play a coin toss game over the phone, for example. It's completely nonsense. But quantum communications allow for such strange things. Okay, they're probabilistic protocols. Okay, so sometimes won't have any answer. Okay, if have like a failure, okay, the protocol can fail sometimes, but some other times the protocol will work, and you can, with fairness, decide, for example, with a couple splits, and they want to decide which one keeps the dog. You can make like this fair coin toss over distance, and okay, so the dog goes to Alice or to Bob. I don't know if this is useful for law,
No,
but maybe, I don't know, some a more complicated version of that, maybe then, I don't know.
It is useful for me because there's a whole discussion currently about fairness into these random number generators, right? But there's this idea of quantum random number generators are very interesting to me because they promote fairness, right? Something that in companies, when involving virtual worlds, this is not often found and sometimes disputed. And it is interesting to me because this is my final question for you, actually. Is this enforceable in any way, or is this too costly for a company to actually do, to put into a virtual online system?
Bernardo, are you talking about looting? Like, for example, why do I get a better loot than the other player?
No, not even just that.
That should be a use for that, Why do I get a better, weapon than the other? That's random, probably, but, I don't know if it's really random, so.
We can even go to casinos with this discussion.
Yeah, casinos.
Something that is very important online.
The problem is this quantum number generator is when you see it, for you, it's a black box, okay? You don't see the internal workings of the device. So you can always think that actually in the inside of that machine is like a USB drive just outputting predetermined numbers that were beforehand generated. And the company that has fabricated the device tells the casino what are the numbers, and the casino can play with odds that are for them. So even if there is a quantum way of generating the numbers, you have to trust the manufacturer of the quantum number generator, okay? The only way of having something that you can untrust the company, the manufacturer, is using this violations of Bell inequalities that I have shown you. So you have to use entangled pairs of particles, like entanglement between photons. And then I have not explained this to you, but you have freedom to choose some parameters to measure, and you can make like a, how do you say that? You can prove, you can certify. Yeah, it's a certification.
It's like an audit. You are auditing it.
Yeah, exactly. Exactly. It's like an audit. You can audit the numbers. You can verify for yourself that the numbers are really random, even if you do not trust the manufacturer. This is something that quantum physics also allows, okay? You have to use entanglement for that. And of course, it's much more expensive than $1,000 because you have to have this source of entangled photons. And the source that I know of entangled photons costs like $50,000. Okay, so
pocket money. Pocket
money for big companies, sure, not for us. But yeah, it's possible. Okay, it's for this area of auditing. It could be used.
Perfect. That is just, thank you so much.
My dear Elisaveta, you do have a question, right?
Yes.
We combined the
Some
question.
Questions, yes. But first of all, thank you so much. It was amazing. I really admired by your effort you're trying to make it easy for us. With all
That's
these
right.
funny examples. Thank you so much. I want to ask the question about blockchain.
Okay.
Yes, because I heard the rumor is that the quantum computer is the threat for blockchain. We had this conversation with my colleagues because we wrote an article about blockchain.
Mhm.
And yes, and I said we better be hurry in writing it, in publishing, because if quantum computer is a threat to blockchain, yes, the article could be useless when it will be published.
No, it would be useless. Yes, the quantum computer can be a threat to blockchain in this following sense. Blockchains usually use what we call one-way functions. Like when you multiply two prime numbers, it's very easy to know the answer. Okay, you take one large number, you multiply by the other prime number, which is also large, and you get a really, really big number. It's very, very straightforward, very easy to calculate. But the inverse function is very, very hard. It's factoring. Okay. In Shor's algorithm is able to do this opposite calculation, taking a very large number and find the prime factors of the number. This is what which is called in mathematics a one-way function. Blockchains also use one-way functions. As far as I know, Bitcoin's blockchain uses a kind of hash function. So a hash function is a kind of one-way function. If you take a word, for example, a series of characters, and you calculate the hash of the series of characters, it's very easy and it's really, really fast to know the hash of a certain sentence or a certain group of characters. But the inverse function, I mean, the inverse hash is really, really difficult. And that's why there are so many miners using a very huge amount of power, of computational power to mine Bitcoins, because the Bitcoin problem is to find a certain string of characters that when you append to this string the previous element of the blockchain and you create, you calculate the hash, the first n positions of the hash are 0. Okay, this is the Bitcoin problem. So if it were easy to make the inverse calculation of a hash, then well, Bitcoin's problem is already solved. I have the hash with, I don't know, 6 zeros in the beginning, and I do the inverse hash, voila, I have the answer, and I have my Bitcoins. And of course, if you can create a quantum algorithm that is able to do this inverse hash function calculation, of course, some kinds of blockchains are going to be affected, okay? All the blockchains that are based on proof of effort, that you have this hash function and you have to make effort. The only way known today is making this in a hard way, trying many words until you have the hash with the starting n zeros. So you have to do this it's like a brute force approach. The brute force approach is exactly what the miners use today for approving the new elements of the blockchain and getting Bitcoins for them. For the case of Bitcoin, Ethereum, this big cryptocurrencies, but there are different models of cryptocurrencies that had already been discussed. I don't know much about blockchains, and this model of Bitcoin, I know it's not very environment friendly because you spend lots of power. The last article I read about that is the amount of power used to mine Bitcoin today is comparable to a small country. It's insane the amount of power required to mine Bitcoins. So there are different models of blockchains that are being developed. They're more environment friendly. Maybe these new models will not suffer from this problem, not be based on a brute force approach, and then a quantum computer won't be able to do much. But this algorithm that inverts the hash It doesn't exist, okay? So you don't need to be worried about your article because it doesn't exist yet, okay? Maybe someday someone will develop an algorithm that makes this inverse hash calculation, but no one knows, okay? Maybe in 1 month, maybe in 10 years, we don't know.
Yeah, but
So-
you know the problem with Scopus publications, yes? Sometimes you
No,
have to
no
wait.
problem. Yes, exactly.
Thank you.
Guilherme is a CNPq researcher, official researcher in Brazil, you know, so he's one of the few of them, right? So he knows
Yeah,
about
there are
Scopus
a few
papers.
hundreds.
He published in English, and you know, it's different than usually people in the legal field that we rarely publish in English. Not us here, but engineers, they only publish in English since they have
Yes.
2 years old. So it's so he Scopus, because Elisaveta loves Scopus. If you, hi, my name is Daniel, she asks you, do you have Scopus? You know, she's, you know.
Okay. Okay.
Yes,
Yeah, but no worry, okay? No worries for the moment.
okay.
Okay, a quantum computer cannot break any blockchain for the foreseeable future.
So my article is safe
Safe.
now. Okay.
It's safe, yes.
I also
Does
want
anyone
to
has, you have any more questions? Go ahead, Elisabeth, floor is yours. Go ahead.
No. I would better give this opportunity to the students.
Okay.
First, you, please. Do you have any further questions? You're the boss here.
Okay. The first question of mine was from me as a specialist in law and digital technologies, but I'm also study business law. So another question will be from this area. So do you have special programs of support of the research in quantum computers in Brazil? Because I know that in Russia, we do have this grant support specifically for quantum computers. Maybe you do have something like that in Brazil.
We don't, unfortunately.
No?
No, we are in, especially now with this government, the amount of resources for research as a whole. Okay, not research in specific areas like quantum computing, but as a whole, the amount of resources available for research, I think it has dropped like 90% over the last 2 years. So actually, this is a political project. It's not, something that happened by chance. There's something going on that really wants to, take money out of the scientific research and put in different areas. So no, it's very different from Europe and from the US. Europe has many lines of research. For example, inside Horizon 2020, there are many specific budgets for quantum information as a whole, quantum communication, quantum computing, and so on. But in Brazil, we don't have anything, unfortunately. And when we do get some small calls for research projects, the amount of money is usually, very, very small. We could never, for example, have money to build our own quantum computer. We wouldn't have hundreds of millions of dollars for a quantum computer, never.
But
Completely
Guilherme
out
can
of the
partner
question.
with Russia, Elisaveta, so you can partner with him and you can get the Russian grant.
Yeah, we could partner with anyone, actually. No problem.
After all, we are the BRICS, so it's
sure.
it's always a strength,
We're
right?
still the BRICS.
Yeah.
Because if things continue to move the way they are moving, maybe in the future it won't be anymore. There will only be the RICS left.
Take the B out.
Yeah,
Never.
take the B-
We stand.
the
We
B out.
stand. Brazil's
Yeah.
here.
Yeah.
And which country is the leader now in quantum computers?
I don't know.
USA?
I don't know, because there are many companies. There are many big companies that invest in quantum computers. In China, for example, they have Baidu, Baidu is investing huge amounts of money in quantum computers. They have already built their own quantum computer, but it's kind of a secret. And they have, some field of research. There's a guy over there in China. It's called Zheng Wei-Pan, and he has like armies of students working for him, and they have already developed some kind of network of a kind of quantum network that uses satellites and optical fibers, and it has been spread, I mean, for thousands of kilometers in China. So China is investing a serious amount of resources in quantum computers. Europe, but I don't know the difference between the countries. In Europe, Japan also, and of course the United States. The first company actually that developed a quantum computer was a Canadian company called D-Wave, and they are still in business. And I think they have been bought by Google or something like that now. Google, of course, is investing billions of dollars in quantum computers as everything else. So I don't know. The answer is I don't know, but there are many big players in the market now.
Andrea, Elia, any further questions? Because I'm just saying your names because you have your camera open, so it's, you have the first row of questions. If you show your face, you can ask questions. That's the rule. No?
That's a good rule.
Right now, there is no question, but the presentation was very interesting. Yeah, it's very actual. And actually, I don't know why, but there is no any information about quantum computers in educational system. We don't study anything about it in physics, for example, and well, that's strange.
That's true, because quantum computers are new, relatively new. For example, this cloud solution of IBM, I think it was created like 4 years ago. So before that, it was impossible for a regular person to have access to a quantum computer. So quantum computers were only, theoretical things. So this is all very recent. And I think that with time, the basic courses on quantum physics, and, they will start to incorporate some aspects of quantum computation, and the students will start learning things about quantum physics using the quantum computers, not the other way around. Yeah. Today, first we study quantum physics, and then we apply our knowledge of quantum physics to quantum computers. And I think this will be kind of reversed in the near future. People will learn quantum physics using quantum computers. And I don't think this is far from now. Probably in the next 5 years or so, this will already be used in many universities. Even in PUC, I have a course in like introduction to quantum computers. That is an elective anyone can do. I mean, not anyone, because we stress that it's important to have a minimum background in linear algebra and in physics, okay? But we don't require anyone to have studied quantum physics before. We just ask them to know the basics of linear algebra, because the calculations use vectors and matrices and so on. So you have to know how to make these kinds of calculations. And a minimum about, no, sorry, not physics. We asked them to have at least an introductory course on programming, because they have to use Qiskit, which is based on Python. And in PUC, the very first subject, the first course in introduction to programming uses Python. So we asked them to have this course before. So as you can see, there's no prerequisite in physics of any kind. Just with the basic knowledge of maths and programming, we teach them how a quantum computer works and so on. I really believe that this is going to be more and more, found out everywhere. People will start using this for educational purposes. And IBM has a special license for educators. So because when you run something on a quantum computer, there's a kind of a queue. Okay, you have to be in the line for there's kind of priority for requests to run algorithms on the quantum computer. And if you have this special license, you can kind of go first. You have kind of a preference for going first in the priority line of quantum computers. So they are already thinking about that. IBM is already thinking about that, and I think the others will follow.
Elisaveta, any more questions?
We do have a supercomputer or high performance computer in South Ural State University. So I maybe better go and say my colleagues not to use this high performance computer anymore, but continue with research in quantum computers.
Well, I think the high performance classical computers will still be really, really useful for a long time, for a long, long time, because there's still a long road ahead of for quantum computers. When they really become useful, when we have thousands of qubits in a quantum computer, that will take a long time. I think IBM has made an announcement last week saying that until 2039 or something like that, they have the intention of building a quantum computer that does something really useful. So we are talking about decades in the future. So your colleagues in the high performance computer, they have many things to do until this moment arrives. Okay.
And 1 year from now, we'll see Apple launching the quantum iPhone, right? 1 year from now, out of the blue,
no,
quantum iPhone. That's.
But I really think that maybe Apple is investing in some kind of quantum computer, because all big companies are. So Apple is trillions of dollars worth, right? So of course they can take like pocket money, as Daniel said, and invest in quantum computers. I don't think they will be out of this dispute of this track, for deciding what will be the future model of quantum computing.
Yeah, they cannot be. It's their business. No one in this business can get out of it. Yeah.
Exactly. Yes.
They might be hiding it. They are good in hiding their projects.
But probably Apple will have the fanciest quantum computer, right? The one which looks better and there's a better interface, better user interface, not necessarily the best hardware, or I don't know.
Elisaveta is a Microsoft lady, right? You don't like Apple, Elisaveta, right? I'm just kidding. She'd love. Who doesn't like Apple? Who doesn't like Apple? If you like Android, you prefer Android, you are in the wrong research group, man. Oh, Bernardo has Android. Sorry, Bernardo, you can stay. Okay, any further questions?
I may have just one last question, because Elisaveta was talking about hash. That's currently what I'm researching about. We're talking about blockchain before, right? And you said to us that blockchain, because currently there is an algorithm that is focused on this whole, let's see what I wrote here, this whole inverse hash thing, right? Since there's nothing yet that could potentially affect this, any articles we write about this won't be in danger of becoming useless anytime soon. But exactly. about inverse hash reactions, we all know today that, at least I don't know if you know this, but in hash today, in companies, we use hash as a way to protect the, how to say this, the identity of a product. Like for a design of a car or a clothing line, for example, we have the whole ledger thing. I'm not sure about this exactly. You may know this better than me. But this whole idea of a ledger using hash, where we get the specific identity of that design, or that, let's say, a contract or that signature of that company. could that be in danger anyway, or is this the same thing as blockchain? It's not a problem yet, only in the future.
No, for the moment, there's no danger at all.
Great.
For the
All right.
moment, it's impossible. Okay, not impossible, unpractical. It's not impossible because there's no mathematical theorem that says explicitly that it's impossible to invert a hash function. Okay, people know it's very hard to make this inversion. It's kind of something that people know because they know. Okay, they have worked with it for decades and they know it's really hard, but there's no mathematical proof that it's hard. So in principle, it's possible that tomorrow someone will wake up with a really good idea of doing that, okay? And if I were this person, I wouldn't tell anyone because I would be killed instantly, because I would destroy the current cryptography systems employing in the whole world. I would be in danger, of course. So I wouldn't, go to the world and say, I have found out a fast algorithm for inversing hashes and finding the prime numbers of a huge number. I wouldn't. I would keep myself, probably. I don't think you are in danger at all.
All right. Thank you so much. That was it for me. Thanks.
Elisaveta, please finish our session. Final remarks. It's all yours.
I didn't want to finish this session. That was really remarkable. Thank you so much. I just want to say to the students, to the participants of this group that yes, this topic is really, really promising. And from the legal point of view, there are so many unresolved issues. And if some of you guys, you like this topic, yes, there are really, really a lot of unresolved issues. For example, the cybersecurity aspect or the aspect of the competition law, yes, and so on. So maybe, yes, if somebody would like, let's do it. It will be cool. Thank you so much again. It was awesome.
Okay, thank you. Thank you everyone for the invitation. It was a pleasure to be here. And if you have any further questions, Danielle has my email. I can put it here in the chat. You can send an email to me. Okay. Well, thank you.